Okay. Now I did. And you guys can see the slides, right? Okay. Okay, so there's a lot of slides here. If we don't cover them all, we'll cover them next week. And I posted an assignment that you're going to do that's due in 2 weeks. It's due on the 27th. So we're going to do some of this math and some examples there. So the definition of Six Sigma is going to be really 6 standard deviations. So how many of you have had some statistics? Okay, and a couple of you I think have not, and that's okay, because we'll get there. Sometimes I think it's better if you don't have it, to kind of cloud all of that. So the one of the premises about Six Sigma is that things are in normal curves. So is everybody familiar with a normal curve, that bell curve, which is the shapes that you see here on this? So the Six Sigma is the standard deviation. Now, the standard deviation when it comes to statistics is the amount of variation under that curve. So we've got a target and we've got some spec limits that we're going to look at. And generally we start with that. We say, this is the target dimension that we're trying to get. So Six Sigma is all about things that are quantitative, measurable, so that we can actually take measurements. We're going to either measure the length, the width, the height. We're going to measure the weight. We're going to measure the circumference or the diameter or whatever it is, but it's something that we can measure in the process. It can be time. It can be, you know, an actual physical dimension of whatever we're making. So we're going to do that. And we're looking at, so that we have a target, this is what we want to do. And then typically when we do specifications, when we write specifications, when designers write specifications, they write things like 10 inches plus or minus a ½ inch, or 10 inches plus or minus a quarter of an inch or an eighth of an inch. So, and they do it in like 0.125 for an eighth of an inch. And so they have a target that's in the middle, and then they say plus or minus, so it can be either way a little bit. Occasionally you'll see specifications that say +0 minus this, or plus 0.25 minus 0. So it might say, that says it's got to be at least the dimension that you're looking for. Can't be less than that if the minus is 0, but it can be a little bit bigger than that. So then what we do typically in manufacturing is we say, okay, we're going to move our target a little bit so that we have more of this bell curve that we can get. So the designers do that for different reasons, but we're usually trying to shoot for being in the middle, right around a desired target. So here's our target. And we want to end up with this blue line kind of thing, much more than we want to end up with the green line. And why is that?
It looks like the green line's I guess most best is less frequent than the target. Like the curve kind of the apex of that curve is towards the lower spectrum of the target, and it doesn't, as it goes closer to the target, it seems to be like kind of impossible to achieve that.
Yeah. So I just misspoke and I said we want to be more blue than green, but there's aspects of both that we want. So we want to be like the blue line, where we're centered around the target, where our apex here is pretty much in line with the target that we have, right? We're not exact. You can just kind of eyeball this and say, I'd like it to be probably just a little bit more to the left, but it's pretty close, right? So we have our and the curve indicates that all of the values we have are underneath the curve. So all of the things fall within that, and it measures the dispersion and the variation of our values. And I'll show you what that means in a little bit. But we're trying to get this curve so that when we plot it all out, it's going to be centered around the target. Now, so the blue is better because it's centered around the target. Now the green is better because it means we have tighter variation. We have less variation in our process. Our distance between the bottom, can you see my cursor when I do this?
Mhm.
Yes. Okay. So the distance between the tails, which we call the ends of this, is a lot shorter distance than the blue one, right? So it means we have less variation and things are centered more around that. So we have a higher quantity of things centered around the middle. The problem with the green one is it's not centered around our target. So we would like to move the green one over a little bit and be more centered around the target and tighten the blue one up, because what you can see here is the blue is going to bleed over outside of our specification limits
Mhm.
on either side. And we don't want to be outside of our specification limits. We want to be inside. So what we do with statistical process control, or Six Sigma, is we use a charting process, and we chart these and we calculate not specification limits, but we calculate control limits. So we want to say, how good is our process? How repeatable is it? How frequently do we get parts in the right range of dimensions that we want? And how far apart do they vary? So from, if we're going to make 1,000 parts, one right after the other, we'd like them to all be the same, but we know that they're not going to be exactly the same, but we want them to be as close as we can to each other, so that we have this a curve that's more like the green one, which is less variation. We don't want to use, we have a spec limit, but we don't want to use a spec limit. So we're going to start with our target and our spec limit. We're going to design our process to produce products to that. And then we're going to measure it to see how much variation do we have. And we want to have our control limits well inside our specification limits. Because if we don't, if we can have a process that's in control, but if we're outside of our specification limits, then that means we're going to have a process that's in control, but it's making parts that aren't going to meet our specification, and so aren't going to be usable in our process and our next steps. So if this isn't making any sense, please just bear with me, and I think we'll get there. Okay. So, and again, if we don't get through all these slides tonight, because there's quite a few of them, we'll get through them next week, and I'll give you some time to look at that. So that's the Six Sigma. So what we're looking at is this standard deviation, which is a calculation, and you can, there's a formula in Excel, if you know how to use Excel, that will give you the average and the standard deviation of a range. And we can look at that a little bit if we have time, and if you want to do that at the end of class. But what we have is, again, here's our process average. Here's our lower limit and our upper limit. These are calculated limits. These are control limits. It doesn't say that, but it is. And we calculate those as being Six Sigma out. And we want to look at how many values this represents. So if we have a Six Sigma process, it means that we have 6 standard deviations on either side of the mean. And that's going to give us that's going to calculate to 3.4 possible defects per million opportunities. So we don't have to make 1 million parts to get there, but it's going to tell us that our process is good enough that that's what we would do. Now, most processes don't need Six Sigma quality. If you think about, I always have my water bottles. If I think about my water bottle here, is there anything that really would need to be only 3.4 defects per million? I've got a couple of things here, right? I've got the lid and I've got the labels. Obviously, the labels don't have to be Six Sigma, and this one is pretty poor. It's kind of peeling off. So that's not a big deal. As long as it's printed, the information is correctly. I don't know if you can see this, but it's got wrinkles in it. Some gaps here where it wasn't put on smooth, but that doesn't affect my water, right? It doesn't affect what I consume. Now, this lid needs to fit pretty well there, and it needs to fit tight enough so that it doesn't leak. but that's not too hard. And that doesn't have to be Six Sigma quality either. If my parts are designed correctly and I have a low variation in my parts, I'm going to be able to screw this lid on and seat it properly. How about the water inside here? Does the water have to be that pure and meet all those specifications?
Yeah.
How pure is the water in my water bottle? This one's empty, but that's because I just put it in my cup.
Mm.
Is that water? Does it have anything else but water in it?
Oh yeah, yeah. It would have, depending on the source and you know, the pipelines, and there's a kind of established limit to how much particles of that can be. It's like it's measured.
Right.
The
Yeah,
particles.
we can measure that, right? So
Yeah.
what kind of stuff is it okay to have inside my water bottle?
You have I think it's like the sodiums. There's like sodium chloride, if I'm not what is it? There's chlorine, or you know what I mean?
Yeah, that's all good. So sodium chloride is typically salt, right? So
Yeah,
and there's all kinds of minerals in there, right?
yeah.
Sodium chloride, there could be some what'd you say, sulfur, sulfides. There
Yeah.
could be some iron and some different things. Now, we don't want a lot of that in there, right? If it's too much, if there's too much iron in there, what's the water going to taste like?
It's gonna taste like blood, really.
Yeah, it's going to taste like, and it's going to taste metallic, right?
Yeah.
And it might smell like that. What else might make the water not seem palatable? What other kinds of contaminants or minerals or whatever?
I used to study all this.
So sulfur is one, right?
Yeah.
What
Yeah.
does sulfur smell like?
It smells like rotten eggs.
Rotten eggs, right? So have you ever had your water that smells like funny, like a little bit like rotten eggs?
Yeah, from the tap.
From the tap, sometimes it does. Yeah, depending on where you are, which is why a lot of people drink bottled water here in Southern California, because sometimes we have that. It's not necessarily bad for you. And if you took a shower in it, you would maybe notice it, but it's not going to affect anything to a certain level, of course. You don't want, overkill, but it doesn't have to be 3.4 parts per million. It can be more than that, and you won't even notice it. So, but at some point, you're going to start smelling that sulfur. So you don't want that, because that doesn't smell good. Now, there's a lot of things that can be in there. Zinc, and think about all the kind of minerals that you take, that people take, not necessarily you guys, but people take in terms of vitamins. You take calcium, you take iron pills, you take magnesium and zinc and all these other kinds of things. And actually we want a lot of that in our water, right? Because what happens to your body if you drink distilled water?
It's like through osmosis or something, it starts to the water starts to take the minerals out of your cells, because of it starts to flush the electrolytes out, like the minerals.
Right. It's not good for your body to drink a lot, really to drink much of distilled water at all, which is pure. But we want distilled water for certain applications, right? And when you want distilled water, when you want it to be pure, that you're going to rinse something off, or you're going to use it in a medical application, then you don't want all those other things in there. And there are applications for that. But for the water that we drink, we'd like it to be better tasting than tap water, which is why they have filters where they take a lot of the things out of it that make it taste a little bit not good. And then it's fine to drink. Now there's things like arsenic and cyanide, and we don't want any of that in there either, right? So even a tiny, tiny bit of that can make you pretty sick. So and anything that you might be allergic to, we don't want. So they're going to filter that and look for certain things. If there's a little extra calcium in it, or maybe zinc, it's probably within a range. Again, you're going to have specifications that say this is allowable, then it's going to be okay, because that's fine. And we need those minerals and those electrolytes in the water to keep our bodies healthy. If we have distilled water, it's not good. So not everything needs Six Sigma quality. If we're looking at things like making vaccines, making drugs of any kind, then you probably want pretty close to that kind of quality, right? But when you make your car, do you think your car is anywhere near 3.4 defects per million? And how many things could be wrong on your car? Or not, I shouldn't say that. How many things do you think you're going to measure on your car? Think about the dimensions, right? Think about your doors and your hoods and your side plates and everything. Do you think all of those are within 3.4 defects per million? No. They're going to, because the car is able to absorb that, right? You've got some tolerance in there. Doesn't have to be perfect. It can be well within the tolerance limits and still not have that kind of quality. So if you look at the paint on your car, if you look at it very closely, you'll see some drips and some pooling and things, especially along the bottom edges of the car. And if you open your door, typically you can see some overspray in there and things like that. So you could find a lot of defects, but we want to say this is really good quality. So when we talk about Six Sigma, it's 3.4 defects per million opportunities, because you don't have 0.4 of a defect. You either have a defect or you don't. So you would have 1, 2, 3, 4, or 16 defects in your lot size. So this is in the sample, in the population that we're trying to assess, how many things that we're building. So that's what we're trying to do. So within one standard deviation, we've got 68% of our values, which is okay, but probably not very good. Within 2 standard deviations, though, and you can see where this goes on the curve, we've got 95%. And within 3 standard deviations on each side, we're finding that 99.7% of the values fall into that. And so this 3 Sigma quality is often very acceptable levels of quality for what we're trying to do and trying to manufacture in a production environment. So you have to say, what kind of level do we need? You can get better, but if you get better and you don't need to, then you're spending extra money to do that. And it gets harder and harder to increase these levels from 68 to 95 to 99.7 to 3.4 per million, which looks like this: 99.999997. I'm sorry, the 9998. So we don't need all of this every time. So where do we need to be? And many companies are fine with saying we're even in between this 95.46 and 99.7. So that means we have pretty high quality, and a 99.7% quality is pretty good in just about anybody, except for these extreme kind of things where we really are looking for microbes and things like that. So what we have is we have a chart, and what we do is we chart this. So the idea is that if we're going to make things, and we're going to make things in volume, we'd say we're going to make 1,000 of them. If we make 1,000 of something, we don't want to have to check all the dimensions on all 1,000 parts, right? That's going to cost us a lot of money. So it's not going to be very lean if we keep measuring all of these parts. And if we're making them sequentially, and we have a process that's allowing us to do that, even if it's a pretty manual process, if we have trained people, they should be making parts consistently. So what we're trying to do is to see how consistently can we make these parts. So what we're going to try to do in this is we're going to say, all right, we're going to take a sample of this. If we make 1,000 parts, we're not going to measure 1,000. We might take a sample of, and we might say, let's make them in batches of 200. So we're going to make 5 batches of 200 parts, and we're going to check some parts in each of that batch. So we're going to have 200 parts, and within that 200 parts, we're going to randomly identify parts to be actually measured and checked. Now, there's a statistical process that tells you how good you want to do this and how many what samples you should take. And then it gives you an allowance for if you have a reject. Because if you take a sample and you might think, okay, I'm going to have 200 parts, I'm going to take a sample of 12. If any of them are rejects, then I reject the whole lot. But that's not necessarily so, depending on what level of quality you want. So there's charts that you can look at to say, if I want this level of quality, I need to take a sample size of this, and the number of rejects I can have in that size is 0, 1, 2, 3, whatever the statistically it comes out to be. So we could go into all of that, but we're not going to go to that. I'm just going to tell you there are tables where you can find that information and you can use that. And they're going to tell us how many samples to take. And then we're going to measure the samples. So and then we're going to chart those on what we call a mean or an average chart. So if you haven't had statistics, you all know what the average is, right? You just take all of the values, add them up, and divide by that. The mean is the average. So there's a couple different terms that we use in statistics, but we're going to focus on the mean, which is the average, and that's a pretty simple calculation. So in this chart, what we're going to do here is we're going to say, all right, we're going to calculate, our target is going to be 80. So this is our target line, this blue line in here. So we're going to say, all right, now we're going to calculate, we're going to take some samples. In this case, we've got 6 samples. Do we have 1, 2, 3, 4, 5, 6, 7, I guess out here. We've got 7 dots. So we're going to take 7 samples, and we're going to measure those, whatever we're measuring. Let's say it's the diameter of something. We're going to measure that, and we're going to take that average. So, okay, we take their samples and we add up, say we take 10 samples and we add those, we take the measurements, we add those up, and the average size is 79.5. So we're going to plot that. And then for the second lot that we have, we're going to take another 10 parts. We're going to measure those. And when we add that up, it comes out to be a little over 80. So 80 point maybe 2 in there if I kind of eyeball this. And lot 3 looks very much the same. Lot 4 is not quite 80. So the average of that is going to be a little bit lower. Here's the lot 5, which is right on that 80 number, which is looking good. 80.4 here, and then we've got down to 79.5 right in here. So those are representative. They're the average of the sample, the dimension on the samples that we took. They're not, so that's representative of that lot. So then what we do is we calculate the average of that. And in this case, our average is going to come out at 79.96. So if we take the average of all these numbers, then our number is going to be 79.96. And that's pretty close to what we want for 80. So that says that's pretty good. And then we're going to calculate these, and these are our spec limits. So we've given that 81.25, it looks like, and 78.75. So it's going to be 80 plus or minus a little bit. Now we're going to calculate our control limits, and our control limits are this blue line, and it looks like it's this one up here. So we've got our control limits set, and we're within our chart, so everything's good to go. So that's what we're trying to do, is to come up with this chart, and we do this over time, and we track it, and we look to see, we calculate the limits, the control limits, not the spec limits. The spec limits are what the designers give us to say this is good. We calculate our control limits, and we make sure that our control limits are inside our spec limits, and we'd like for them to be getting closer and closer together over time. But as long as we're within that, we're doing well. So we're moving along pretty well in that regard. So then we also want to look at things, and we want to say, we want to understand the range. And the range is going to be the difference between the high value and the low value in the sample that we took. So in this one, we say this was our sample one, and our average of the dimensions that we took there, we measured that was 79.5. And then we're going to say, all right, now in that sample, what's the high value? What's the low value? And let's take the difference between that. That's the range. So it goes from the lowest value to the highest value. And in this case, that's going to be almost 2.5 inches. And this, well, 2.5 of whatever it is. So 2.5 here, the range here, a little bit less in this lot, a little bit here, and here and here. So we're going to plot those. And then again, we're going to take the average of all of that. So then we have 1.867 is our average of the ranges in these sample sizes. And the reason we do that, I'll show you in a little bit, because the range tells you something different than the X bar tells you about where that normal curve is falling and all of that. And then we have formulas where we calculate upper and lower control limits for ranges as well. So then we're saying this is the range we want to stay within. So if we see something that's way bigger than that, smaller than that is not a problem. But if we see something that's way bigger, then we say, okay, now we have something that's going on with this process. So we're losing control. We're not going to be in control on this process. And we've got too much variation. So when we talk about the Lean and Six Sigma, we talk about getting rid of the waste, and we talk about continuous improvement. So both of those apply to Lean and Six Sigma. But with Six Sigma, we say we're also trying to reduce the variation in the process. And we're actually measuring that statistically. So, and that will help us indicate that we're reducing the weight. So it's one way that we can actually track and measure that. So we're looking at different phases of quality assurance. So we have controls here. And if we just are looking at a process and a company that's not very sophisticated when it comes to quality, they're going to be doing lots of inspection. They're going to be doing inspection, maybe that incoming inspection that I was telling you that one company was doing. They're going to check parts. And this always just slays me. So if I'm a customer and I'm buying parts from my supplier, and I trust them and I'm counting on them, relying them, and I'm paying them to send me good parts, why should I have to check the parts when they hit my dock to verify that they're good? To me, that is a huge waste, because I'm paying that supplier to send me good parts, and I've sent them my specifications, and I've said, this is what is a good part. So you need to make parts for me that are to these specifications. And if they can't do that, then you should find another supplier. But a lot of companies use incoming inspection processes, which means they won't accept the parts until they've actually verified that they're good themselves. And I think that should be a rarely used exception, but that's me. And that's, again, thinking in a lean kind of way, because that's an extra inspection that you really shouldn't have to do, because you're paying your supplier to do that. You're paying your supplier to send you good parts. So if you're doing that, you're in a not very progressive part of the quality assurance continuum. If we have quality built into the process and we have this culture of continuous improvement and tools to do that, that's progressive. And in the middle there is our process controls, where we're doing some inspection and corrective action during the production to make sure that we stay on track. And a lot of companies are in this middle area. They can't quite get to this continuous improvement area where everything goes, you just turn it on and run it and everything is good. Most companies are in this, do some kind of checking interim. So inspection is something that we do that we compare the goods, and it's usually goods. Services are hard to inspect. So we compare the goods to the standard, which is the specification that's given to us by whoever determined what this product is supposed to be. And when we think about goods, it's, you know, the height of this bottle, the height of the lid, the gap in the between the lid and the bottle. It's you know, the volume that it holds, it's the thickness of the walls of this. It's all of those things, and many of those things are measurable. So what we're trying to do is to understand how much do we inspect and how often do we inspect it. And then we say, where in the process do we inspect it? So we want to probably check it at the end, but are there any interim places that we might need to inspect before something happens? And then do we inspect it in line in the production line, or do we have to take it off site? And then finally, what are we going to inspect? Can we measure something? So do we have variable data, which is measurable, quantitative, or are we inspecting attributes, things like paint drips and scratches and things like that? So let's talk about this a little bit in terms of, you guys all know how a house is built. What's the first thing you do on the house? If you're going to build a house, what do you do first? After you have land and you have plans?
Foundation.
Yeah.
The foundation. And so how would
Get
you,
rid of the plant.
I'm sorry?
You get rid of the plants and you even out the land, right?
Okay. Yeah, you have to set it all
Well,
up.
yeah, when my dad like bought some land back in the days, you know, you had to get rid of the plants, you had to even out the land, because building a foundation on an uneven land is not really going to work out.
No, you're going to get an uneven building.
And the plants as well, you got to get rid of the plants.
Right.
And also make sure if there's like no water flowing under. I
Okay.
think that's like,
Yeah, so you might do like a soil check or something like that. But if we check, so if we've done all those checks, removed the plants, evened it out, graded it and all that kind of thing, and we pour the foundation, and the foundation is typically made of what?
Cement?
Cement, concrete, right?
Yeah.
Now, how do we check how would we check the foundation? How might we make sure that that foundation is correct?
we like measure.
Don't you want to make sure it's like level? Like it was poured properly and evenly?
Okay, so let's take those one at a time. What would we measure, Nikon?
Well, like the width and the height of the cement. I mean, it depends on what you planned on doing.
Yeah,
Let's say you plan on doing like 5 feet of width and you come out with 6, right?
then we have a problem, right?
Then we have a problem.
So we have a specification that tells it's supposed to be this long and this wide and this deep, right? So we can measure those things, right? So it's pretty easy to measure the length and the width, but how do we measure the depth?
I feel like you'd have to measure that before you start pouring.
Yeah. So you'd have to say, all right, let's make sure our hole is big enough, right? If we're supposed to have a 6-inch foundation, if we only start with a 3-inch hole, then we are not going to get a 6-inch foundation, right?
Mhm.
So we can measure that, we can set that up, and as Nikon said, make sure it's all even and everything. And then we could actually put something in there to measure that we can pull out and say, hey, did it actually get to be 6 inches? Or put a little marker on the edge of it, say, you know, 1, 2, 3, 4, 5, 6, so that when the concrete comes up to the 6 inches, we know where it is. So that we could do that. So we can figure out how to measure that, and it's easy to measure the length and the width. And then Nanar, you were saying things like the smoothness of the top, right?
Yeah.
So, yeah, so you want it leveled out, and depending on what it's supposed to be, it needs to be more level, or it's okay to be a little bit not so smooth. So there's ways to make it really smooth, and then there's ways to just kind of let it be concrete and whatever. If you, for example, if you have concrete countertops in your home, those are typically really smooth. They're not rough, right? But some applications of a foundation need to be can be left a little rough. If it's a garage and it's going to be exposed, you want it to be pretty smooth. So you have to say, what's my specification? And then what does this look like in regards to that? So we can check all of that. Now, do we want to check the foundation before we do anything else to build the house? Yeah, why?
Because that's basically like your support. You're building everything on it, and that's what's gonna, it's the support. Yeah.
Because if that's not right, nothing else is going to be right, right? You're whatever you're building at the end is not going to be right. If we needed 6 inches and we poured an 8-inch foundation, we might say, oh, this is probably going to be okay. It's a little more than we needed. We can live with that. But you have to weigh all those things against everything else. What is my specification? And then what is my actual value? So that's going to tell us that we need to inspect that. And then what if you're going to build a house, what do we do next?
You'd have to, I mean, there's the walls, but then there's also the utilities too that you have to install, like the plumbing, like a lot of underground stuff you have to lay it up. If necessary, if they're not already laid, the pipings before you start
Well, that
putting the
better be done
walls.
before we do the foundation too.
Yeah,
right?
yeah,
So
yeah.
let's make this simple and say that it's going to be like a garage that doesn't have any drains or any plumbing in it.
Okay, yeah, definitely the wall.
Then we go to the walls, right? Now the walls are framed, right? They're like 2x4s. And so we put those up and we make the frames, and then so we have that. And then we can run any electrical wires or anything through that, right? So we can see, we have that. Now, if we want this to be really nice looking, we might want to say we're going to put drywall on the inside. Now, at what point do we inspect? What's the next inspection point? So we put the frame up, and now we've run all the electrical wires. We're going to put the drywall up. Do we want to inspect it after that, before that? What do we want to do?
Inspect before
Before what part, Peter?
the drywall,
Before the drywall. Why?
because electrical needs to be up to code. And if
Because
it's
you
not,
can't. Yeah.
you're up to drywall.
And we can't see that if we put the drywall up, right? We can't see what's back there. So if we put the drywall up, all we see is a wall. We say, oh yeah, that looks really good. But we can have the wires all going the wrong way and everything upside down and wrong. And so no, you can't put that on. You can't put the drywall on until you've had the electrical wiring inspected. And if you have plumbing too, for sure, because you don't want that. And you want the plumbing in the right position relating to the wires, because both stuff goes through those walls. But like, you don't want plumbing and pipes to sweat and drip down onto electric wires, because that's a recipe for disaster, right? Water and electricity don't go together well. So you want to keep them apart. And if anything, you put the wires some distance above the pipes that might sweat and drip. So we're deciding what points we're going to inspect. Then if we make this house or this garage, say, we're going to, we've done the framing, we've inspected it, we put the drywall on, maybe we've started putting the outside wall on, then we have to put the roof on, right? So it's the same thing with the roof. You put the roof on with those big triangular pieces, and you get the inspector to come out and look at all that before you start finishing it, because you need them to be able to say it was done correctly. If you start slapping on shingles before the inspector comes out and looks at it, he's not going to know, or she's not going to know, if the roof was installed correctly and if it's going to last, or if it's going to be falling over in the wind or something else. So we have to decide when we're going to inspect things. And there's some natural kinds of things, and I'm using a house rather than a production process, but you can think about what you might need. So you don't want to, if you're going to cover something up, you want to inspect it before you cover it up. If you're going to join something like pouring the foundation, you're going to check it before you're going to let the foundation set up and make sure it's done correctly. Because if you don't mix concrete right, you're either going to end up with slush, or you're going to end up with something that sets up too quickly and is going to crack and be too brittle, right? So you've got to get this just right. So we're going to say, when do we do that? So some other things to think about is if we glue two, if I staple two pieces of paper together, I can, and it's not done right, I can take the staple out and put another staple in, right? So that's something I can repair. If I glue two pieces of paper together, that's really a process that's not going to be undone. That's kind of an undoable process. Think welding, right? If you weld two parts together, can you take them apart? If you don't weld them right, can you take them apart?
Yeah.
You can take them apart. Can you weld them back together?
I don't know about that.
Yeah, generally no.
Yeah.
Because you've changed that. You have the welding, fuses the materials together. You can cut them apart, but if you try to fuse them back together, it's not going to do the same kind of thing. So you got to think about when you want to inspect in your process and what to do. And then if I'm back to my house example, I can do certain things to the concrete where it is in place, right? But if I really want to test and say, was that mixed correctly? I'm going to have to take that. I'm going to have to get a sample of that to a lab to let them do their test, and they do it what they call a destruct test, which means if it's supposed to take this much weight, they actually press weight on it until it cracks, until it buckles, to say this is it does do what it's supposed to do or it doesn't. And you can't do that to the foundation that you poured, right? You don't come out and take a jackhammer and say, oh, this is not supposed to crack until I put this much pressure on it, because you can ruin your whole foundation. So you pour a sample at the same time and you send that sample to the lab. They can do the testing there, and then they come back and say, yes, it's good or not. So there's different ways to do that. So where we're going to inspect it, if I'm inspecting it on site, like I'm going to inspect my electrical and plumbing and things, that's on site location. If I have to send it to a lab, that's going to be a centralized or an off-site location. And then we're going to, like I say, we're going to look at what we can measure. If we can measure it, the length, the width, and the height, then that's going to be variable data. That's quantitative things that we can measure. If it's an attribute data, then it's going to be how smooth is that floor. So there's a couple components if we want that nice smooth finish. One is how level it is, but the other is just how smooth it is. So we might have a little leeway in how level it is, as long as it's smooth and it's not detectable that it's going up and down and up and down and up and down, right? If it goes very gently down and then up, we might be okay to not have it perfectly level, because getting it perfectly level is frankly pretty tough. But we don't want it in such a way that it's going to pool water if there's liquid on it. But sometimes you want it with a little bit of a curve on it, so that things run off and they run toward maybe the drain in the area. So like if we had a drain where we were going to put a water heater, so we want a drain there, we might want that to have we want it nice and smooth, but we don't want it perfectly flat, because we do want it, if there is drip drainage from that water heater, we want it to drain toward that, toward the drain. So what are we trying to do with it? What are the specifications and how do we get that? Does this make sense, what we're trying to do here? Okay, good. I'm not just talking crazy then. Okay, so what we try to do is to figure out how much we want to inspect. And the real optimal area comes in because we want to inspect enough to make sure that we don't pass defectives on to our customers, or that we don't continue making bad parts after some point in time. Like, we don't want to start framing the building until we know that the foundation is good, because if the foundation has to be repaired, dug up, replaced, or whatever, we don't want to have to undo a lot of other work. So where is our cost of passing defectives, and then how much would escape this, and then how much does our inspection cost? So we're looking for that kind of cost benefit analysis. We could keep inspecting everything and make it down to the 10th of a millimeter, but do we need to do that? No. If we're framing a house, we need the walls to be fairly straight, but they don't have to be, they need to be spaced, but if they're off a little bit, that's okay. There's certain dimensions that are more important than others, and those are critical to function dimensions. And so we want to look at those. So where we're going to inspect raw material, purchase parts, finished products before a costly operation like putting a roof on, before an irreversible process like welding, and then before we cover something up. If we're going to cover it up, then we want to check it before we put the lid on it, or we put the we aren't able to see it before the drywall on, so we can see it. So we talked about this. So we're going to use this statistical process control, because this is what's going to help us do this. So when we've decided we're going to use not a lean approach, but a statistical process control approach, we're going to say, okay, we're going to look at our process. We want to say, do we have random variation in there? So what would random variation be?
Is that like if you're pouring the concrete, the random variation of where you stop pouring?
Where you start pouring?
Stop. Like
Stop.
how much is in the thing that you're pouring it into in the end?
So the variation would be in the measurements we take. So if we're trying to get a 6-inch depth of the foundation, we're probably going to measure in more than just one place, right? We're not going to just pick like one corner and measure that. We're going to pick different points around the perimeter that we're laying to make sure it's all 6 inches. So then we're going to say, okay, how much difference do we have in those measurements once we take them? So we're looking for the variation. That's all supposed to be 6 inches, and we're going to get some numbers like 6.2 inches, maybe 5.9 inches, 6.1 inch, or something like that. So we're going to say, are these variations random? And if it's non-random, if it's random, then can be stable. It doesn't have to be stable, but it can be. If they're non-random, then it says we've got a problem. So if one side is all under 6, it was supposed to be 6.0, but it's coming out like 5.8, then it says we probably have a problem, because that whole side is 5.8 and it should have been 6. So if we had a little bit of variation in there, but we don't, it's definitely, so it says we dug the hole too shallow. So we didn't drill it, we didn't dig the hole enough and make sure we had the leveling done correctly. So that's what we're trying to say, is we're looking for the variability. Do we have random variation, or do we have non-random variation? And if we have a stable process, is the variation within a range that's acceptable to us to do that? So if we have say we have a house that's 20 by 20, a big slab that's 20 by 20, 20 feet by 20 feet. We're going to take some measurements, and we're going to look at the depth of the concrete, and it wouldn't be surprising to see that 6 inches plus or minus like 1/10 of an inch all the way around it. So if we have variation like that, it's probably going to be okay. If we have between, say, 5.5 and 6.5 inches, that's probably too much variation to say that we have a good foundation, because it's not going to be very level or very even, and that's going to cause problems down the road. So you have to determine that before you start your process. So the random or the common cause variation is the natural variation in the output, because there's lots of factors going on, especially when you're doing something outdoors. You could have, a rock underneath this, or a clump of soil. You could have the wind blowing in at one area, or something. You can have a bug that lands in your concrete, or some kind of animal or something that made some difference there. So there's a lot of minor factors. But if we have assignable variation, then we can identify the cause of that. So my example of every one side, we took, say, 5 or 6 different measurements, they're all 5.8. Then it says, hey, we got a cause here that's causing all of these to be that. And it's probably that we just didn't dig this hole big enough, didn't flatten that out to make this a 6-inch foundation. So SPC says, statistical process control says, we're going to take periodic samples of the output and compute these sample measurements statistically. So we're going to look at the average of the samples. We're going to take some measurements and do the averages. And then we're going to look at how many occurrences we're getting that are either good or acceptable or bad in our rejects. So that's what we're going to do. So our sampling plan says they're part of this control process. We're going to look at defining, we have to understand what we're going to control. So this is very similar to the DMAIC, but we're going to define what we're going to control. We're going to say, what can we measure? How are we going to measure it? Compare the measurements to the standard, evaluate that, anything that's out of control, put some corrective action in, and then monitor to find out if the corrective action that we determined is going to work really does work, and if we got rid of the problem, or if we created another problem, or if we just didn't hit what we were trying to do. So we're going to figure that out. So the control charts are this plot of the samples that we're going to do. And so we're going to chart these, and there's a lot of software that does this today, but you can also do this in Excel. And so do all of you have access to Excel and know how to use Excel a little bit? Okay, because some of the homework is going to be like that. So we're going to calculate some control limits. The control limits are the lines between the random and the non-random deviation. So it's going to tell us where is our acceptable limits to have this much variation in the process. They define that range of acceptable variation. They are not the spec limits. The spec limits tells us what's allowed by our design definition. And if we have a process that's in control, then our control limits are going to be inside our spec limits, and we're going to be able to keep working. So in this case, this is a similar chart to what we've seen before. We're going to calculate our controls, and anything that comes out, if we're going to calculate the control limits, and then we're going to keep measuring and keep plotting. So if we find this value that's outside of the control limits, we're going to say, uh-oh, we got a problem here. So this is our out of control identification. So we're going to stop our process at this point, and we're going to say, okay, what happened here? Now, sometimes we can say, oh, we know what happened here. The machine, somebody bumped into the machine and it had an error, or we had a power shortage kind of thing, or somebody spilled something on the keyboard here and that made this problem. So if we know what that is, then we can throw that value out and say, okay, we still have a process that's in control because we know what happened here. We know that it has an assignable cause. So we know what happened, and we can say, all right, it doesn't affect our process because it was outside of the normal range. If all of a sudden we start getting readings like that, values like that, we got to say something's going on here. So we got to stop the process and figure out what it is. So we're looking at what's assignable cause, what's normal variation, which is that little bit of up and down versus something that's clear outside of those limits once we've calculated those. So we're looking for kind of errors in the process. And the type 1 error says we have a process that's not in control because of the analysis we do, but it's actually in control. So what happens is if we get this value and we say, okay, now we determine that we have a process that's not in control. So that means we need to go take some corrective action. We need to make some changes. But if this truly, in hindsight, is just one of those things that it happened for a reason that we can determine, and our process really is control, that's called a type 1 error. And this is a manufacturer risk error. So if the manufacturer, the supplier, and I say, oh, my process, I determined when I looked at it, I did my calculations. Now I say my process isn't in control, then I'm shutting down, I'm spending time, money, I'm not producing, I'm not getting my customer orders filled. So that's my risk because I shut that down for that reason. Now, the other side says that we say, oh yeah, the process is in control. So we look at a situation like this. We say, yeah, we know what this is. It was just one of those fluke things. And we really are in control, but it's not, then that's the consumer risk. Because what happens there is we say, oh yeah, it's okay. We continue making parts. We continue shipping parts. And guess what? That this is eroding in the wrong direction. And it turns out that we have had a problem and we didn't find it. Our customer finds it. And you don't want your customers finding your quality products, your problems, right? That's not a good thing. So that's the consumer risk. So when we look at it in terms of statistical bell curve, the type 1 is going to be out here. So we find things out here. This is the manufacturer's risk that says, oh, we don't think it's in control. And really, it's all fine because most of it is under here and there's not enough area under these curves to cause real problems. That's the 1-2% kind of thing. When you look at 99.7%, it's the 0.2 or 3%, or it's the 1 or 2% that you are going to get back in returns from your customers that says this has a problem, which most businesses can live with. 1, 2, 3% is okay, and you're not going to lose enough customers with that kind of error rate. But if you have things that gets out to the customer and 20% of them come back, it's going to cost your company a lot of money. So we want to be in that error range. Then here's the difference between the range and the X-bar chart and the range chart. So you can see we have different delta with different parts here, different sample size values. So here's 1, 2, 3, 4. So we're kind of up and down. If we drew our curve, we're still pretty much in the same curve. We've got a little bit of difference. This one's getting a little fatter, but we're pretty much in the same area. So we're growing that over time. We're checking that. And we're looking at things that we measure. So again, variable data is things we measure. We use the X-bar charts and not the R charts. But we use the R charts too because where is that chart? This is what I'm looking for. So in this case, we have X-bar charts. And if we get values that look like this, we're going to say our X-bar chart, we're going to calculate our means and do our charts, and we're going to say what's happening here. So in this case, on this top chart, the X-bar chart, you can see our data is going higher and higher and higher and higher. So we would say that's a trend, right? We're getting higher values for every sample. But our range looks pretty good because we're still within our control limits for our range. So what this tells us, if you have this kind of combination, it tells us that we're keeping our curve the same size, basically, and the same amount of variation. Sorry about that. I'm drawing on the wrong one. So we're in the range right here. So this looks good, but this says, okay, we got a problem because we've got this trend and it's getting worse. So what it tells us is our mean, our average is moving. So the process is shifting upwards. So if you think about like drilling a hole, if you have a drill bit, what happens if you drill, what happens to that drill bit when you just keep drilling holes after holes after holes? Say it starts out as a 1/2-inch hole. What happens over time? Are you still going to be drilling a 1/2-inch hole?
You talk about the drill bit?
The drill bit, yeah.
No, I guess not. It starts to wear out.
It starts, yeah, well, wear out and wear down, right?
Yeah.
So because of the friction, if you start out with that hole being a 1/2 inch, over time, and it's a lot, it's not just 3 or 4 times you would do it, but if you did it 300 or 400 times, and it's going to be a very small amount, and you hope that the drill bit doesn't break, but after so many uses, that drill bit that started as a 1/2-inch round is going to be down to under a 1/2 inch, right? It's going to be a 1/2 inch minus like a 1/10 of an inch, and then a 1/15 of an inch and whatever. So it's not going to go from a 1/2 inch to a 1/4 inch very quickly, but if you keep using that drill bit, it's going to wear down. So what happens is, if you're measuring that hole diameter, your holes are going to get smaller and smaller, right? It's not going to be a 1/2 inch. It's going to be less than a 1/2 inch because your drill bit wore down a bit. And so it can't drill if it's not a 1/2 inch in diameter, it's not going to drill a hole that's the right size. So you're going to track that over time, and your again, your average is going to get smaller and smaller. So in this case, it looks like it's getting larger, but that's an example of what this would be is, oh, your drill bit's wearing out. So now you need to go fix the drill bit, right? But our range is okay. Now, in this case, we're looking at the X bar chart and it says, hey, this looks good. We're staying within the control limits, no problem. But look, our range is having that problem where we're getting bigger and bigger range measurement with each sample size. So this is increasing. So what this is telling us is we're going from a nice, those first two charts that I showed you, the nice tall green one, we're getting flatter and flatter, which means we're getting more and more variation. So the process variability is increasing. We've still got the same average. We're hitting the target, which is good, but we're getting more spread out, and that's not necessarily good. So I know this is a lot to put out there, but I'm going to stop there. We'll look at this next week, and then we'll go through this some more because there's some more slides in here. Hopefully this is making sense and you guys aren't totally lost. If you're totally lost, like I say, stick with me. We'll get you through it.
All right, Miss, you have